A spinning wheel looks exactly the same, no matter how far you rotate it. That's not a coincidence. It's the defining property of a circle. In this video, we build circles from that one property and prove several genuinely useful facts about chords along the way. A circle is simply the set of every point in a plane that's the same fixed distance from one center point. That fixed distance is the radius. A line segment joining any 2 points on the circle is called a chord. A chord that passes through the center is called a diameter. The longest possible chord. Circles have complete rotational symmetry. Rotate one by any angle, and it looks identical, unlike a square, which only looks the same after 90-degree turns. They also have reflection symmetry across every single diameter. Fold a paper circle along any diameter, and the two halves match exactly. How many circles pass through two given points, A and B? Infinitely many. And every one of their centers sits on the perpendicular bisector of AB, since that's exactly the set of points equidistant from A and B. But through three non-collinear points, there's exactly one circle. Its center is where the perpendicular bisectors of any two sides meet. This is called the circumcentre, and the circle is the circumcircle of the triangle formed by those 3 points. Now the key chord theorems. Equal chords subtend equal angles at the center. If AB or DE, then triangle, key AB and triangle CDE share 2 radius sides plus the equal chord. So by SSS congruence, the angles at the center must match too. And it works both ways. Equal angles at the center force equal chords by the same congruence argument using SAS this time. Drop a line from the center to the midpoint of any chord, and it always hits the chord at a perfect right angle, because that splits the isosceles triangle formed by the 2 radii into 2 congruent halves, and chords of the same length always sit at the same distance from the center. Again, from that same congruence logic. Flip it around. The longer a chord is, the closer it sits to the center with the diameter itself. The longest possible chord sitting exactly on the center at 0 distance. Let's use this with real numbers. A circle has radius 13 centimeters, and a chord is 24 centimeters long. How far is it from the center? Drop a perpendicular from the center to the chord. It bisects the chord, leaving 2 12-centimeter halves. Now we have a right triangle. Radius 13 as the hypotenuse, half chord 12 as one leg, and the unknown distance as the other. By Pythagoras, 13 squared minus 12 squared is 169 minus 144, which is 25. So the distance is the square root of 25, exactly 5 centimeters. Same method works for any chord. Half the chord, form the right triangle with the radius, solve for the missing side. Quick check. The question's on screen. Pause if you like, but try it first. 10 seconds, go. A chord 6 centimeters from a center with radius 10 centimeters. Using Pythagoras, half the chord squared plus 6 squared equals 10 squared, so half the chord is 8, making the full chord 16 centimeters. The answer is 16 centimeters. A circle is just every point at a fixed distance from a center. Equal chords always mean equal angles at the center and equal distance from it, and longer chords sit closer to the center. Free notes in the description. Next video, arcs and cyclic quadrilaterals. Subscribe to Clarix.